In this video, I want to begin introducing you to organic compounds and to some of the simplest kinds of organic compounds, and those are the hydrocarbons. Now, I've mentioned before that hydrocarbons are molecules that are composed only of carbon and hydrogen. In other words, they have no heteroatoms. So hydrocarbons can be divided into two broad categories, which we call aliphatic and aromatic. Now, the term aliphatic is not going to mean much to you until I define for you the term aromatic, and we are not going to do that until much later on in the semester. But I want you to just sort of tuck this term aliphatic away in your brain, and just be aware that everything that we're going to talk about in this video refers to aliphatic hydrocarbons. I'm also going to introduce you to nomenclature, and nomenclature is a very large and very important part of this course, because if you and I are going to communicate and talk about organic molecules, you're going to need to know how to name them, what to call them. The names for hydrocarbons are the simplest names, so we start our students off on hydrocarbons when they are learning nomenclature. So it's a good place to begin. I've already mentioned that hydrocarbons contain only carbon and hydrogen, and today we're only going to be discussing aliphatic hydrocarbons. So within aliphatic hydrocarbons, we can divide these into several different categories. First, there are the alkanes, and I've already talked to you about the formula for a hydrocarbon, which has no double or triple bonds or no rings, and that formula is CnH2n plus 2. And a good example of this, and the simplest example, is the hydrocarbon CH4 or methane. We also have the cycloalkanes. So a cycloalkane is a hydrocarbon in which the carbons are incorporated into a ring. And we also have no double bonds in the cycloalkanes. And this fits the general formula CnH2n. And a nice example of that is C5H10. So we have a pentagon here. This would be a skeletal representation for C5H10. We have 5 carbons because we have a pentagon. And each of those carbons has 2 hydrogens, so that's 2 times 5 or 10. For a total of 10 hydrogens. Then we have the alkenes. So we have the suffix ene for alkene. That represents a double bond. These have the same formula, CnH2n, that the cycloalkanes have. That's as long as you have only one double bond. An example of that is C2H4. And here's the structure for C2H4. We have a carbon-carbon double bond in this molecule. Finally, we have the alkynes, and the suffix YNE is meant to represent a triple bond. They have the general formula CnH2n minus 2. That's as long as you have only one triple bond. And an example of that, or the simplest example, is C2H2. This molecule I'm showing you right here with a carbon-carbon triple bond. We call that molecule acetylene. When you see the suffix ane, you're always going to think no double or triple bonds. When you see the suffix ene, you're going to think double bond. And when you see the suffix yne, or ine, you're going to think triple bond. Now, I've already told you that the alkanes can be divided into 2 groups. They are the acyclic, or no rings. We say that these molecules are fully saturated in that they have no rings and they have no double bonds. So when we talk about saturated fats, what we mean is that's a fat, a molecule that has no carbon-carbon double bonds. The cycloalkanes also have only single bonds, but we have our carbons incorporated into a ring, and because when we go from acyclic to cyclic, we lose 2 hydrogens, we say that these cycloalkanes have 1 degree of unsaturation, and that's 1 degree of unsaturation for each ring. So let's look at some of our alkanes and let's talk about the way that they are named. Now, I've already mentioned to you that when you see the suffix ane, you're going to think no double or triple bonds. You could have a ring. Now, the way that we name them is according to the number of carbons that they have. We've already talked about the methyl group and some of the molecules that we've looked at in previous videos. Whenever you see the term meth, that's going to refer to one carbon. So methane, one carbon, no double bonds. Obviously, you can't have any double bonds if you only have one carbon, but that's beside the point. Our next alkane is ethane, and whenever you see the prefix eth, eth, that refers to two carbons. Ane means fully saturated, or no double or triple bonds. So ethane. And these very simple, small alkanes are the major components of natural gas. This is where they're found. Methane is 90 to 95%. Ethane, 5 to 10% of natural gas. Now we move on to larger molecules. We have 3 carbons in a row, and the prefix prop represents 3 carbons, followed by ane, tells you that it's fully saturated. We have no double or triple bonds. The prefix bute represents 4 carbons, followed by ane, tells you no double or triple bonds. So I think you're kind of getting the idea for nomenclature of alkanes. You have a prefix which tells you the number of carbons, and you have a suffix which tells you that you have no double, whether or not you have double, triple, or single bonds only. Ane means only single bonds. So pent is for 5 carbons, pentane. Hex for 6 carbons, so this is hexane. Hept represents 7 carbons, heptane. Oct, 8 carbons. Nonane for a 9-carbon chain, and decane for a 10-carbon chain. Now these are all the numbers or the prefixes that you are going to have to know. You're going to have to know 1 through 10. And you'll also note that I've put the molecular formulas over here in red on the right side, and you will, if you sit down and actually do the calculations, you'll see that they all fit the same general formula, CnH2n plus 2. I want to talk a little bit about isomers. So you've had 1 or 2 videos on constitutional isomers already. If we think about C4H10, you may recall that there were 2 ways that I could arrange all of those 4 carbon atoms, and these are the 2 ways that I'm showing you right here. So these are 2 different molecules, and that means that they have to have 2 different names. The straight or unbranched chain that you see on the left, we often refer to as being normal. I would call that molecule normal butane, or usually what you see is the N in italics before the name butane. Now, since the structure on the right is an isomer of butane, it's actually the only constitutional isomer of butane that you could come up with. We call it isobutane. An isobutane is a branched hydrocarbon. And remember that these molecules are constitutional isomers. So just as a reminder, isomers are 2 or more molecules that have the same molecular formula, but somehow they differ in structure. Constitutional isomers differ in their connectivity, and you've done a couple of videos on constitutional isomers. We'll learn a lot about geometric isomers a little bit later on, but geometric isomers are isomers that have the same connectivity, but they differ in the 3-dimensional arrangement of their atoms. So we'll talk about that a little bit later on.